Let us recall definite integrals first. The operator dx indicates that we should integrate with respect to the variable x, and the lower and upper numbers beside the integral symbol indicates the integration bounds. So here our bounds is from x is equal to a to x is equal to b. Now what if we consider now functions with two variables, say x and y? So not only do we integrate with respect to x, but we can also integrate with respect to y. So the double integral here means that we should integrate first the inner integral. So here integrate first with respect to x. And in this case, our bounds for the first integration is x is equal to a to x is equal to b. After we integrate the inner integral, then that is the time wherein we now integrate with respect to y. And the integration bounds are y is equal to c and y is equal to d. Now how about the geometric interpretation of the integrals? Recall that the definite integral of f of x from x is equal to a to x is equal to b computes for the area of the region bounded by y is equal to f of x, the x-axis, and the lines x is equal to a and x is equal to b. How about for double integrals? Let us consider graphing f of x, y on the three-dimensional space. Let us say this is the portion of the graph of f of x, y. And let us project this on the xy plane. We only consider the region bounded by x is equal to a and x is equal to b, and y is equal to c and y is equal to d. So that would give us a rectangle, and we denote it as bracket a, b times bracket c, d. The first bracket gives us the bounds for x, and the second one gives us the bounds for y. Upon doing this, we now have the solid bounded by the graph f of x, y, the rectangle r on the xy plane, and the planes derived from our integration bounds. And the double integral of f of x, y with this integration bounds computes for the volume of this solid. So for single integral, it computes the area of the region. For this one, for double integral, it computes the volume of the solid. Observe that in our double integral, the operator is dx dy. We can also have dy dx. Let's consider that in our first example. Let us compute for the double integral of 6x squared y minus 1 with operator dy dx in this given bounds. So what we do here is first integrate the inner integral. So we integrate first with respect to y. So we don't have to mind the outer integrals first. If we integrate with respect to y first, that means our variable x will be fixed or will be seen as a constant. So we can just copy 6x squared and integrate y. If we integrate y, we have y squared over 2. Now let us integrate negative 1. If we integrate that, we have negative y. This is a definite integral, so we will not write plus constant c. Rather, we evaluate from y is equal to 0 to y is equal to 1. If we evaluate at 1, we have 3x squared minus 1. And if we evaluate at y is equal to 0, that will just be 0, so we don't have to write it. And now that we are done integrating the inner integral, we now integrate with respect to x. So this time, we will not treat x as a constant. So we can now integrate with respect to x. We get x cubed minus x and evaluate this from x is equal to 1 to x is equal to 2. Evaluate first with respect to 2. We have 2 cubed minus 2 or 8 minus 2 minus 1 cubed minus 1 or 1 minus 1. If we simplify, we get 6. Now let's move to example 2. How about if we have the same function, 6x squared y minus 1, but we integrate with respect to dx dy. That means we integrate first with respect to x. After that, then we will integrate with respect to y. If we integrate with respect to x first, then y is seen as a constant, y is fixed. So we are just integrating here x squared. If we integrate x squared, that is x cubed over 3. So 6 over 3 is 2. Therefore, we write here 2x cubed y. Integrate negative 1 with respect to x, we have negative x. Then evaluate this answer from x is equal to 1 to x is equal to 2. Just a side note, we always write the variable x is 1 and x is equal to 2 because we have two variables here so that we know which variable should we substitute the bounds. Okay, let's go back. Let's evaluate first at x is equal to 2. We have 2 times 2 cubed, that is 16. So 16y minus 2. Next, let us evaluate at x is equal to 1. We have 2y minus 1. Then after this, we now integrate with respect to y. Of course, we can simplify the integrand first. 16y minus 2y, that is 14y. And we have negative 2 minus negative 1, that is negative 2 plus 1. So we get 14y minus 1. And if we integrate 14y with respect to y, that is 14y squared over 2, or simply 7y squared. Then we also have minus 1. If we integrate that, we get minus y. Then evaluate from 0 to 1. Evaluate at 1, we have 7 minus 1. Minus evaluate at 0, that is just 0, so we don't have to write it. Therefore, our final answer is 6. In example 1, when we integrate our function with respect to dy dx, we got the answer 6. But integrating with respect to dx dy, we also got 6. So the differences here in our examples are, we interchanged dy dx to dx dy, as well as the integration bounds. This is a result of Fubini's theorem, which states that if f is continuous on the rectangle a comma b cross c comma d, then the double integral of f with respect to dy dx is equal to the double integral of f with respect to dx dy, given that the integration bounds are also interchanged. Fubini's theorem would be really helpful if we integrate, let's say, with respect to dy dx first and saw that the next solutions would be difficult, so you then change to dx dy. Or vice versa, if you find integrating with respect to dx dy difficult, then you can change it to dy dx. So always remember that when we use Fubini's theorem, first what we have to do is interchange dy dx to dx dy, or vice versa, as well as the integration bounds. So let's consider this third example. Let us integrate y sine of xy with respect to dy dx. So here, the inner integral is with respect to y. So we integrate first with respect to y. So how do we integrate with inner functions again? Recall from our previous lesson that we use integration by substitution. So here, our inner function is xy from the sine function. So let u be equal to xy. Since we are integrating with respect to y first, then we will get the derivative of u with respect to y. So du is equal to x dy. But if we substitute this in our given, yes, we have sine u because we have sine xy. But how about y dy? We cannot put du in our given because there is no x dy in our original integrand. So what we can do here is we use Fubini's theorem. In using Fubini's theorem, our function will not change. So we can just copy y sine xy. First step is interchange dy dx to dx dy. Then second step is interchange the bounds. So 0 and pi will be the outer bounds and 0, 2 will now be the new inner bounds. Now let's integrate with respect to dx dy. That is, we integrate first with respect to dx. So same thing, let us let u be equal to xy. Then get the derivative of u with respect to x now. That would be du is equal to y dx. So here our earlier problem is solved because y dx is now in our integrand. So we can use this substitution. Before we substitute, let us first change our bounds as well. Our bounds are x is equal to 0 and x is equal to 2. If we want to change our variable to u, then we also have to change our bounds to u. Substitute x is equal to 0 in u, we have u is equal to 0. And substitute x is equal to 2, we have u is equal to 2y. So sine xy would be sine u, y dx would be du, the bounds 0 to 2 would be 0 to 2y, then just copy the outer integral sign and operator dy. Now let us proceed in integrating sine u. The integral of sine u is negative cosine u. And evaluate this from u is 0 to u is 2y. We have negative cosine 2y minus negative cosine 0. Cosine 0 is equal to 1. So we have minus negative 1, that would be positive 1. We can just let negative cosine 2y as is. Then we now integrate this with respect to y. Let's eliminate a few lines in our screen so that the board looks neater. Now let's integrate the last line. We have an inner function 2y. So we again use substitution here. Note that we already used the variable u in our previous solution. To avoid confusion, let us use a different variable, say v. Let v be equal to 2y. So our integrand would be negative cosine v plus 1. Be careful that the plus 1 in our integrand is outside the function cosine. Now what will happen to dy if we differentiate v with respect to y? We get dv is equal to 2 dy. That means dy is equal to 1/2 dv. Substitute this in our integral, so we get 1/2 dv here. Now what will happen to our bounds? The bounds 0 to pi are the bounds for y. So we also have to change it for the bounds of v. If y is 0 and y is pi, then v would be 0 and 2 pi. Note that 1/2 is a constant. We can just put it outside the integral sign. So let's write 1/2 here. Then proceed with integrating negative cosine v. The integral of cosine is sine. So we have negative sine v here. And the integral of 1 is v. So we have plus v. And if we evaluate from 0 to 2 pi, we have negative sine 2 pi plus 2 pi minus negative sine 0 plus 0. Sine 2 pi, sine 0, and 0 are all equal to 0. Therefore, we have 1/2 times 2 pi, or simply pi. Let's consider more examples. Let us evaluate the double integral of 4y squared x dx dy with respect to these given bounds. Here we integrate with respect to x, but first let us consider this integrand. Our integrand is equal to 4y squared x. And with respect to x, 4y squared is a constant. A correction, that is not 3y squared, that is 4y squared. If we have a coefficient which is constant with respect to the variable which we are integrating, then we can write it first outside the integral sign. So in our example, we will only integrate x and write 4y squared outside this integral. In fact, we already did this in our previous examples, but this time, we are also including the variable y if we integrate with respect to x. Similarly, if our coefficient is in terms of x and we are integrating with respect to y, then we can also put the coefficient outside the integral first. So let's integrate this. The integral of x is x squared over 2. If we evaluate from 0 to 3, we have 9 over 2. Copy the rest. Let us simplify 4 times 9 over 2. That is positive 18. Then integrate y squared with respect to y. We have y cubed over 3. And we now evaluate this from 0 to 2. This is equal to 18 times 2 cubed minus 0 over 3. Or simply 6 times 2 cubed. But 2 cubed is equal to 8. Therefore, our answer is 48. For our last example, let us integrate xy all over y squared minus 2 with respect to dx dy given these bounds. Here we are integrating with respect to x first. Thus, y over y squared minus 2 is a constant coefficient with respect to x. Let us write that outside the integral of x dx and focus on integrating with respect to x first. The integral of x is x squared over 2. Evaluate this. We have 4 over 2 minus 1 over 2, that is equal to 3 halves. 3 halves is a constant with respect to any variable. So let us put that outside the integral sign. And now our next step is to integrate y over y squared minus 2 with respect to y. Let's continue on the second half of the screen. Here, we let u be equal to y squared minus 2. If we use this value for u, du would be equal to 2y dy. And this is okay, we can use this because y dy is in our integrand. Now our bounds for y should also be changed to bounds for u. Substitute this bounds in our u, so we get the new bounds 1 to 2. So from our last line, 1 over y squared minus 2 would be 1 over u. Y dy is equal to 1 half du. And the bounds would now be from 1 to 2. And just copy 3 halves outside the integral. We can already multiply 3 halves and 1 half here. So we get 3/4. And integrate 1 over u. The integral of 1 over u is ln u. Evaluate this from u is equal to 1 to u is equal to 2. We get ln 2 minus ln 1. Recall that ln 1 is equal to 0. So this is just ln 2. Therefore, our final answer is 3 over 4 ln 2.